I was trying to do something without words in my title here. So first things first, as part of this presentation, I've asked, we're going to use some personal technology here. If you have an iDevice, the app I'm going to use is called Pocket CAS, and there's 2 versions of it at the App Store. One is free and one is paid. So if that's something you want to load up on a device or pair up with somebody that has that, or any sort of graphing capability would be good. First off, does everybody here have a sticky note? There you go, thank you. All right, so that should get us started here. So I'm the University of Hartford here, and I'm going to demonstrate a very small IBL-like activity that I use with my calculus class. So to give you some context here, I teach a flipped and inverted calculus course. We have about 25 students in our class on average each semester. They watch short videos before class as a preview of content, and class time is spent doing and discussing mathematics. And what I found over the last 2 years of doing this is that by pulling that direct instruction outside of the classroom space into something they do in their own time, it's really freed up some time for me in class to do some more investigative activities. And since I attended this conference last year, I've really tried to incorporate IBL-style activities into my calculus course. I'm very fortunate. I teach in a very technology-rich classroom. I have a personal set of 13 iPads that are loaded with a variety of apps, one of which includes Pocket CAS. I also teach in classrooms with round tables and or square tables, kind of trapezoidal tables that work well as groups. And the classrooms have either 2 or 3 projectors all connected to an Apple TV. All right, so what happens is that students will do work on their iPads, and then we can very easily project their work up onto the board. So I realize that I am in an unusual situation to be teaching in such a technology-heavy teaching space. So the timing of this activity is that students work on the class before we start talking about chain rule. All right, so it's something we do as a preview to chain rule. And they know the derivative of sine and cosine. So they know the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, so I really have 2 objectives here. I want students to make and test a conjecture. I want them to look at some information that I've provided some boundaries for them, but I want them to use this information to make and test a conjecture, and then I really want them to expose them informally to the derivative of composite functions before we go through that formal exposition, introduction to it. Okay. So here's where the sticky note is going to come in. I start off class with a classroom voting question, and I don't have clickers in my classroom, so I do this a couple of different ways, and I thought this would be the easiest way here for this conference. Before I pose the question to you, I want you to think about a student you've had in a class. They could be your top student, your middle student, or your bottom student. You're not going to answer this question as if you are a mathematics professor. I want you to answer it as if you are that student that you're envisioning in your head. Okay, so that's the first thing to hold. So what I do is we start off the class with the question. What's the derivative of sine of 8x? Okay, so what's the derivative of sine of 8x? And then what I do is I'll display the 4 options up there, and somebody reminded me of another option that I don't have. So what I'd like you to do is take your notes and write down either A, B, C, or D on your sticky note. No conversation with your colleagues. And remember, you're pretending you are a calculus student. So think of one student you've had in your class before they've gotten this far, and write down what you think they would answer. And this is really an inauthentic kind of assessment because we hope all of us can do this problem. All right, so this is normally what I do in class, and I'd have students actually take and put their sticky notes up on the wall. I'm hoping this is going to work. All right, so I think people have nicely collated them for me, and I'm not doing very well. Okay, the least interactive, exciting part. Okay, we have, oops. Sorry to whoever I shortchanged. All right, A. Okay, I'm going to just sit here for a second here and see if there's anything else to put up on my chart. I don't think I have seen enough. Oh, there's a B here, wait. Okay, so I have about a half a dozen or a dozen more in here. So every single one of these is an A. All right? So, all right, so every single one of these is an A. So I'm just gonna stop right there. But, so what's my purpose behind doing this? And this is not a rhetorical question. What's my purpose behind doing this? Yeah, what else? Yeah, what else? Anything else? Yeah. So what we're doing here is we're trying to do all of that. We're trying to say, let's take a guess. Let's make a hypothesis about what we think this is going to be. And then we're going to go in and take a look at this graph. It's completely anonymous, right? I have no idea who wrote what on which sticky note. So it gives us a way to start the class and also to help us think about what this is going to look, what are we going to be doing here in this investigation? And we're going to be looking at this particular problem. So this keeps getting revised every semester. I make changes to it, so I don't have any data for that. So where do I start the investigation? I have about 25 copies of the investigation. I have a couple here if we need some more back-end spaces where there are none. So a couple things are important for me to do. I need to review vocabulary. Period and amplitude are some of those things that sometimes students they'll remember those terminologies, but they won't remember exactly what they are when they're thinking about and looking at sine and cosine graphs. I also need to review the decimal approximations for pi over 4, pi over 2, pi, 2 pi, 3 pi, because they're not going to look at 3.14 and change and think, ooh, that's pi. And the reason why we have to do that is Pocket CAS graphs, they give you approximate values. They don't give you exact values for coordinates. I also then give the students with an overview of the investigation. I have them look at it and just take a look at this. We have 3 parts to our investigation here. And then I'll emphasize part 1, because if you look at part 1, it's a little bit tricky. We have 2 groups. I have 2 groups of functions there. So in group A, I have cosine and sine with coefficients greater than 1. And in group B, I have cosine and sine with numbers between 0 and 1. Again, so we're looking at what's the effect of these different parameters on the derivative. And then what I do is I model the process for graphing cosine of x and its derivative, cosine of 2x and its derivative using Pocket CAS. And I do this to make sure all of our students are kind of on the same page. So I'll actually do that for you right now. We'll go through and intro the Pocket CAS. All right. So this is Pocket CAS. This is something I use regularly in my classrooms. I've created a new document, and I'll click on New Entry. It gives me an option to plot. And what I'll do here is I'll type in, we're looking at sine, right? Of 2x. So if I type in sine of 2x, it would then graph it. But then if I hit return, and I would do the derivative, I hit the CAS button down the left-hand corner, and then I do the derivative of sine of 2x. I probably said cosine, didn't I? I don't know what I did. 2x. All right, that looks right. Now I hit go, and it graphs that for me. The free version, so if you look at this is the paid version, which allows you to put 5 or 6 different graphs, functions on one graph. The paid version only allows you to do the free version only allows you to do 1 or 2 at a time. So then here, this gives me an opportunity to talk to the students again about, we're looking at amplitude and we're looking at period. So if we take a look at our sine function, we see that, okay, it looks like we have this is 1 period here, and now I can tap on that intercept. So it gives me, again, so the decimal approximation of pi, so my period is pi. And then I look at my derivative in red, and again, it looked like I had the same period, and then I could verify that by looking at the x-coordinate of that maximum up there. And then we take a look at the amplitude and say, look, here my amplitude is 1, but when I take my derivative, my amplitude is 2. So something is going on here. This is where you get to play. So partner up with somebody that may have an electronic device that can graph something or is willing to go on to desmos.com and look at that. So I want you to, I was thinking about this after sitting in on Victor's presentation yesterday, is think about this both from a student's perspective and from a teacher's perspective, but also more importantly, what kind of modifications or extensions might you suggest to me or any other ideas you might have? Because a lot of times, these kind of activities are called Larissa's crazy ideas because I come up with these little activities and I'm the only one in my department who's kind of saying, oh, let's do this, let's do that. All right, so let's take some time to do that, maybe 5 or 10 minutes. So what I want to do is just give some ideas here of what people were thinking about, because as I was going around the room, and honestly, just to give you a sense of when I teach my class, me going around and listening to your conversations is pretty much what I do with my students. And obviously, it depends upon what we're doing in those classes. So a request I have for you, if you have an interesting piece of feedback, since my brain is gone and I'm very tired after this week, can you take that piece of paper, and if you've got some ideas or suggestions for improvements, just write them on the back and give them to me at the end, because I really, really appreciate that feedback. I so rarely get feedback on stuff I do in my classes, that this is a very valuable experience for me as a teacher. So just some suggestions, some things that people were thinking about as they were looking at these things.
Kind of a counterintuitive, rather than starting with a sign, but just using an odd function. So you have x cubed, but then look at negative x, parentheses, cubed, and then looking at that sort of derivative, it gives you a kind of a counterintuitive, what happens to that negative
What happens
sign?
to that? That is interesting, because we were talking here about trying to find another function that we could use, other functions we could use.
But this was similar to the sign one, except now they don't have to recognize any sort of trig identity.
Right, okay. Victor? Oh, sorry, hang on.
Please say your name before we go.
All right, Victor Piercy. So we thought I don't think extension is the right word, maybe a pre-extension, but you could use this idea to compare the graph of, say, cosine to its derivative. And then you can use that idea to raise the question, why is the derivative of a periodic function periodic?
Okay, good. Somebody, you folks had a suggestion, you gentlemen had a suggestion in the back to using,
Ethan Twisdale. And yeah, we sort of had the idea of maybe you could even graph by hand rather than technology, sort of something like look at the graph of sine of x versus sine of 2x, and they would know what the graph of sine of x looked like, and then you could look at how would the compression affect the derivative and get an idea by hand rather than strictly relying on technology, which might be helpful, especially if you don't have 13 iPads in a class set.
Other suggestions?
Mylan Sherman, Drake University. I use GeoGebra for a lot of my explorations in calculus, and I thought of maybe using a slider for A that could be dragged continuously, and seeing how the relationship changes as opposed to just, and then they have to begin to think about strategically what do I want to put in for A to look for relationships.
Okay, so now I have a reason to learn GeoGebra again. So what happens next with my students? They display the conjectures on the board. They make their conjectures on their iPads and display them on the board. And we discuss their predictions in part 3. And then kind of we return to the initial question, what is the derivative of sine of 8x? And then we ask them to then modify, go back to that original slide I showed you, and modify what they're going to do. And I said the intention is for the next class for students to watch the video on chain rule. And just to give you a sense of how long this is, I try to give this about a half an hour in my class. And I will honestly tell you that the origins of this was me teaching a 2-day-a-week class for 115 minutes and getting to about 45 minutes left of class and saying, I don't want to lecture, I'm not going to lecture, that's not the purpose of this class. What can I make up on the fly to make this work? And then I've tried to revise it over the semesters. Thanks. Any other questions or comments?
David Cusick, Marshall University. There is a nice graphical go-around to show how composition works, where you map up to the y, over to the x, and then use the function, and then go back to the original x, which I think might show the students that the last function is not really being evaluated at the same x that they think it is.
Yes.
Paul Forrester, Alamo Heights High School, San Antonio. I have an exploration that I've used for a number of years with my calculus students where they plot the graph on their graphing calculator of sine and then cosine and show that the cosine is derivative of sine. They plot 3 graphs, sine, cosine, and d of sine.
Yes.
And they match up. And then the next conjecture is sine of 3x. 8x is a little bit too many wiggles, but 3x, they can see that compressing it by a factor of 3 makes the slope 3 times as much.
3 times as steep, yep.
but they'll always conjecture cosine of 3x, and it doesn't work, just like the A didn't
Yeah.
work right there. I voted for A, by the way, since I was in there.
Thank you.
Okay. Then they plot the cosine of 3x, and then they plot the numerical derivative, and it doesn't work. It's got wrong amplitude. So how are you going to fix it? And the answer is you multiply by 3.
Yep.
And I say, okay, that's fine. And then the next one is sine of x squared.
Yes.
Okay, and they conjecture cosine of x squared, usually. And cosine of x squared has an amplitude of 1, but the derivative has an increasing amplitude. And so I say, how are you going to make the amplitude increase? Well, you got to multiply it by an amplitude that is a variable. And so they try x times sine of 3x. And it looks the same shape, but it doesn't go up high enough. It only goes half high enough. So they do 2x cosine of 3x, and it works.
Will you
I
share that
say,
with me?
now, where did the 3x come from looking at the original function? That's why I don't use 2, I use 3.
Right.
Where did the 3x come from using the original function? And the answer is, oh, that's the derivative of the inside function. Okay, go back to the second example. Where did the 3 come from? Oh, that's the derivative of 3x. And right away they know the chain rule. Then the last one is, the function is sine of x to the 0.7.
Yes.
Conjecture what the derivative is going to be. And once they have seen the pattern, they almost always got that one.
And that's actually what happens at the end of the class when they with the conjectures up, is we do talk about where does that coefficient come from for the amplitude of the derivative. And they look at it and they say, oh, it's a coefficient here, but again, let's put this in the terms of calculus. That's actually the derivative of that inside term. And
If you only have 3x as the inside function, 3 is not that. If you only have 3x inside the original function, the 3 is not so clearly the derivative as 2x is the derivative of x squared.
Yes. Yep. Right. I think we're out of time. What? That's the intention of the last problem on the bottom, yes.
I was at your talk yesterday.
Yeah.
And I thought the idea of using the questions that were embedded in the lecture to prepare your next class,
Yep.
I really like that idea. I was wondering if this activity evolved in that way, and what were the types of questions that students were asking that may have motivated you to create this activity?
Initially it really was a matter of I had extra time in class and I needed to find something that was quick for them to do because I wasn't going to lecture on chain rule. And then it kind of morphed into an investigation because I felt that I wanted them to play around with some functions first before we talked about the formal statement of the chain rule and started throwing all those symbols in. So what actually happens, especially the last 2 semesters I've used it, what's happened is when the students walk in after watching that video on chain rule, and now I throw a couple of examples up on the board, I can now draw their attention to what we did with the sine and cosine functions and say, okay, now we're looking at the derivative of x squared plus 1 to the 5th. What's that? So how what we're doing here parallel to what we saw yesterday? And I think it's made that transition easier for them. At least that's my impression of it. Again, I have no evidence to that effect, but.
May I do one more?
Of course.
As
As long as you promise to share
Paul
things
Forrester.
with me. No, as long as you promise to send me things that you use.
You wrote your name on my list. I'll send
Okay.
it. This illustrates the fact that you want them to know what the property says before they go off and prove it. Don't prove something that you have no idea what you're trying to
And
prove.
I just want to have them to have a sense of that you just shouldn't dive in and just automatically assume that I'm going to use these. I have these great rules, and they're probably going to botch them up and use them incorrectly. I think somebody was saying their students would, just take the derivative of, derivative sine is going to be cosine of 8 rather than 8x or something. And just not having them dive in directly and have them think about what the compression does to the graph of the grid.
I like your diving in analogy because I regard proving something as crossing a raging river. And if you just jump into the river, it'll sweep you away. But if you have a lifeline to the other side, which is what you've done with your exploration,
We're trying.
then you have a chance of getting to the other side safely. Once you know what you're trying to prove, then it's easy enough to prove. I do the same thing with the fundamental theorem and a lot of others.
Okay.
Rod Switzer. I'm just curious where the videos are that you're showing your class.
Okay, so I didn't write it on here, but I will actually, hang on, let's do this. It's math.hartford.edu/flipping. And that'll get redirected to the actual site for it, but that's the address of it. And they're very much directed to our students. We don't prove anything in our Calculus 1 class. Right, so that is not the focus of it. We try to give students a sense of how things are working, but not any sort of actual proof, which is a whole matter of discussion with our department currently. But we've opted to not do any proofs at this stage because of our audience. Thank you.